Right, so hello everyone. It's my great pleasure to host this QuTech360 and to welcome Fabio Sebastiano. So let me first introduce our speaker today. So Fabio Sebastiano received the bachelor and master degrees in electrical engineering from University of Pisa, Italy in 2003 and 2005. And in 2006, the PhD degree from TU Delft. In 2011, the PhD degree from TU Delft. Then from 2006 to 2013, he was with NXP Semiconductor Research in Eindhoven, the Netherlands, where he researched fully integrated CMOS frequency references, nanometer temperature sensors, and area-efficient interfaces for magnetic sensors. 2013, he joined TU Delft, where he is currently an associate professor and the research lead of the quantum computing division of QuTech. His main research interests are cryogenic electronics, quantum computing, sensor readouts, and fully integrated frequency references. He's been on the technical program committee of ISSCC, the RFIC Symposium, and the IMS, and he's currently serving as associate editor of the IEEE transactions on VLSI. He's been co-recipient of the 2008 ISCAS Best Student Paper Award, the 2017 DATE Best IP Award, and the ISSCC 2020 Jan van Wessem Award for Outstanding European Paper. He also served as distinguished lecturer of the IEEE Solid State Circuit Society. So it's a great pleasure to have Fabio today, and he's going to tell us about Cryo-CMOS electrical interfaces for quantum processors. The floor is yours, Fabio.
Thank you, David. Yeah, thanks for the nice introduction. I hope most of you guys knows me, has seen me around QuTech, and I hope now that we are getting back to in-person meetings, in-person presence at the university. Well, not today, but to meet each of you later on. So if you have any questions about what I'm gonna say, I'm very happy to answer. Well, after the talk, but also later on at QuTech. So I want to talk about cryogenic electronics. And I want to start with a little bit of history. So if you look a little bit back in the past, not too far, in 51, this was, at least to what I could find, the first use of electronics at cryogenic environments, and was an experiment done at Leiden. And they used a tube amplifier, so not even transistor based, to basically measure some quantities they had in an experiment at low temperature. And the idea was basically to put down at very low temperature the amplifier to avoid interference coupling to the long cable connecting room temperature electronics to the cryogenic experiment. So you can realize already there was basically a motivation very similar to what we do today. And from that moment in time, if you look to at least the amount of papers published about cryogenic electronics, you see, from the 60 onwards, a big increase of papers in this domain. So you see, at the beginning, there was a lot of interest driven mostly by interest in superconductivity and electronics related to that, followed by work on Josephson junction. At a certain point in 1986, you even had liquid nitrogen-cooled supercomputers. So it was commercially available. It was not a big success. You don't see them anymore because Moore's law kept going, so people abandoned this. But now, in the last few years, you see a big spike of work in this domain in electronics at cryogenic temperature, and that is mainly attributed to quantum computing activities. Now, why is that? Well, if you look at a quantum computer today, many of you may be aware, may be familiar with this picture where you have the bulky cryostat with all the wires going to the room temperature electronics. And the question is how this will look into the future to go to large-scale quantum computers. Well, it's nice to make a parallelism or parallel with another system, which is classical computers. So if you look at the computers in the 40s, they looked very similar to the quantum computer we have today. So very bulky with a lot of wires, discrete. And to go from this system to the system we have today in silicon-based classical computers, basically what we did is basically use two inventions. First of all, the transistor, which replaces the tubes, which made the circuit becomes much smaller, but much more important, the integrated circuits, which enabled us to make everything much smaller and compact. And what I believe, and many people I think are together in this thought, is that if you want to go towards a large-scale quantum computer, we have to move out of the scheme that we have today. So today you have the quantum processor, at least for many qubit platforms, has to work below 1 Kelvin. And then you have an electronic interface implemented with bulky off-the-shelf equipment at room temperature. And then you have to wire those the electronics to the qubits. Now, if you want to make something which is a little bit more scalable, a larger scale, so with many qubits, it's much more handy if you can bring the electronics very close to the qubits. So if the electronics close to the qubits, the interconnection problem is gone. So you don't have any more to interconnect long cables and a lot of cables over this interface, which makes the system very bulky, but also very unreliable. And to do that, you have to make your electronics small enough to be close to the qubits. So you need to make it integrated, but also needs to operate at very close temperature. Maybe not the same, but very close. So you need cryogenic integrated electronics. If you want to go there, what are the challenges that we have to address? Well, mainly three challenges. The first one is the performance. So now in many of the setup that you see connected to quantum computers, you have very bulky, top-notch equipment, very expensive equipments, boxes like this. And now we are trying to get performance which are maybe similar to those machines into an integrated circuits. So that's the first challenge. But maybe a better question would be how much of this performance you really need. Performance in terms of noise, accuracy, speed. And why is that a problem? Well, of course, because you can imagine that there is a matter of area. So very high performance, you can think it requires a lot of volume, a lot of functionalities. But it's also true that in electronic circuit, typically you pay to have more performance, you pay with power consumption. So typically, the more performance you want from a circuit, the more power you need to spend. And power is a very precious resource at cryogenic temperature, because if you look to the typical power budget in a dilution refrigerator, which typically hosts these experiments, we see that the cooling power drops very fast as you go to lower temperature. And if you are at the stage where the qubit typically live, around 100 millikelvin or below, you have less than a milliwatt of power consumption. So very little to power to do something with electronics. If you go a little bit higher at 4 Kelvin, so it's still closer to the qubits than 300 Kelvin, but still a little bit farther, you have 1 watt. And supposing that you want to drive 1,000 qubits, you come up with this power figure of merit, 1 milliwatt per qubit. And it's a number that you see a lot in papers these days. People want to target 1 milliwatt per qubit in terms of power consumption of the electronic interface. And again, it's not the final target if you really want to go for maybe millions of qubits, but it's an interesting number. At least for the medium term, reaching this goal could lead us pretty far away with a few thousand of qubits. So this is the second challenge, power dissipation. So you need to make circuits which are high performance and dissipate less power. So they need to be pretty efficient. And third of all, of course, you need to find a technology, an electronic technology which can operate at cryo. And you have their superconducting devices, which are inherently cryogenic. And this works very well for some application. Or you have to go for semiconductors. Now, some semiconductors like silicon BJTs do not really operate at very low temperature, so they're just discarded by that. Some technologies are very used, for example, HAMs, silicon germanium HBTs, they're used a lot for cryogenic amplification, for example. But in this table, one of the technologies that is very special is the last one, is CMOS technology. And I argue that that's the technology which is really different from the others because it offers very large scale of integration, VLSI. What does it mean? It means that you can implement, embed, integrate on the same die a lot of devices. And when I mean a lot, I really mean a lot. So this is, for example, one of the latest processors you can find, the M1 Max microprocessor. It contains 57 billion transistors. And if you really want to push it, the largest system, at least I could find today, is this system from Cerebra, is for deep learning acceleration, where you have 2.6 trillion transistors. So in the order of 10 to the 12 transistors. So a really huge number on the same die. Now, why you need this complexity? Well, because the vision is that we will build computers with millions or hundreds of thousands of qubits. And you can imagine that the electrical interface to deal with this large number of qubits needs a lot of transistors. So that's why CMOS is the way to go. Now, how you design then the system using CMOS? So we are going to use CMOS operating at cryogenic temperature, for short Cryo-CMOS. And the system I envision is a system like this. So you have on one side the quantum processor, then you have to read out the signals from the quantum processor. Typically, you have some low noise amplification. If you read at baseband, you just directly go to analog to digital converter, or you do some down conversion. You go to a digital controller, which depending on the readout of your qubits, decides how the algorithm will progress. Or for example, here you can imagine some quantum error correction scheme being implemented here. And depending on that, you have then the next operation you want to do in qubits via you convert the digital information to analog with the DACs, digital to analog converters. Eventually, you could up-convert them if you want, for example, to generate microwave signals, or you want to do 2-qubit gates with pulsing, and then you go back to the quantum processor. So this is a system in which you have typical feedback loop. For the ones of you who are familiar with electronic circuits, this is very similar to an RF transceiver, where you have a receiving path and a transmit path. And next to that, not to forget that for such a big system, complex system to work, you also need a number of additional support blocks, like references, temperature sensors, power control, and so on and so forth. But how do you really design a system like this? Now, as an example that I also will show later, Ostrich is a chip we designed and for microwave control of spin qubits. And the first step is always find out the specification for such a system. Once you know the specification, you can build a block diagram, you can implement the circuit, design it, fabricate, for example, in this case, in Intel 22 nanometer FinFET technology. And then you go, you characterize it in the electrical domain. And once you know electrically it works, you bring it in together with the qubits and you test them. Now that's the typical flow, but there is a very important missing element, which very often is taken as implicit, which is the models of the device. In typical integrated circuit technology, and this is CMOS, is a commercial technology, the foundries that fabricate these devices have standard device models that can give to the designers so that you can simulate a very complex system. So simulating is very important once you want to build such a complex system. But those models are typically valid only on the typical temperature range. So typically down to minus 55 degrees Celsius. If you want to go below that, you're on your own. So you have to find your own Cryo-CMOS models. Why is this important? Well, it is important because if you take a transistor and, you know, with the typical transistor symbol with gates, source, drain terminals, and the current through it. So if you look at the characteristics of such transistors, so the IDS, the drain source current, as a function of the VGS, this is the typical curve you see. It's typically almost parabolic curve. And if you cool it down your device down to 4 Kelvin, you see that there is a big deviation from the room temperature behavior. And this deviation typically it's maximum at high VGS, where you see there is much more current available. And in this region here, where you see there is a big shift of the curves. And you can quantify that in this way. You can quantify that by extracting the threshold voltage, which is basically the voltage at which the transistors start to conduct. And you see that as you go from 300 Kelvin down to 4 Kelvin, the threshold voltage increases by a lot, 100 millivolt, which is a lot if you compare it to the supply typical of those technologies, which is in the order of 1 volt. So there is a big increase. And in this region, what is more important is the current gain, the beta, which is typically proportional to the mobility and also increases by more than 60% when you go to low temperature. So there is a big variation, which is also seen a little bit more if you would plot the same data on a semi-logarithmic scale, like done here. So to show this region here for very low VGS, which is called the weak inversion region, in which you see that going to 4 Kelvin, you get steeper and steeper curves. And that has a big impact on the circuit design. And if you would plot the subthreshold swing, which is a measure of how steep these curves are, this plot here as function of temperature, you even see that at a certain point, you even deviate from the classical behavior that is extrapolated from in the, the 200, 300 Kelvin region. And there is a sort of flattening off. And this is also not very well understood yet. There is a lot of research going on to understand why this is. Typically, one of the causes of this is attributed to defects, disorder at the interface between the silicon oxides and the silicon surface, because the CMOS device is a surface conducting device. So this just to show you a little bit the biggest changes, but if you really try to list all the possible changes of your device characteristic when you go to cold, is basically you get higher mobility, so more current, which in some sense is good because more current typically means you can go faster. So this is an advantage. The fact that these curves get steeper means that you have less leakage, because when the transistor is off, you have less leakage current. And also the fact that there is a higher slope means better power efficiency, because you can get more transconductance for the same current. You also get lower resistance in your all metal traces, which means that passives like inductors have an higher Q, and lower thermal noise just because temperature is lower. On the other hand, there is the other side of the coin. You have higher threshold, which means less headroom. Again, you have 100 millivolt increase in threshold in 1 volt supply. That's a lot of difference. You have lower gain. The device matches worse. There is significant self-feeding. So there is not only advantages. So the trick here in these designs is to understand what are the parameters that counts, and try to choose architectures of your circuits that rely more on the advantages and try to get away with the disadvantages. So there is a lot of activity now in research on finding out how to properly model all these effects. I'll show you a couple as we go ahead, but there is still quite a big effort needed to get models which are comparable with the ones that integrated circuit designers are used to in the normal operating regime. And again, it's important to have good models because you want to simulate such complex systems. If you have a billion transistors, you want to be able to properly simulate. You cannot handle such a complexity just by hand. Now, in the rest of the talk, I just want to go through all this system and show you a few examples of some blocks that we have designed or that are just designed in the group, just to give you a feeling of a few problems and some state-of-the-art results. Now, let's start from this part, the microwave drive. So suppose you have a spin qubit in a quantum dot in silicon, for example, and you want to drive a single qubit rotation, which basically means apply a microwave pulse at a certain frequency, which matches the Larmor frequency of the spin qubit, with a certain phase, which determines the axis of rotation of the block sphere, and then the amplitude of the pulse and the duration of the pulse determines how far you rotate on the block sphere. So you have these 4 variables, parameters: the amplitude, the duration, the frequency, and the phase. And what you want to understand is the specification for each of those. So typically, if you have a room temperature setup, what you try to do, you try to buy the best AWG, the best microwave generator, and what you do, you just get the best in terms of noise, accuracy, and so on. But if you go again to an integrated circuit implementation, you want to find the minimum that you can allow. And for example, what you could do is calculate the infidelity as a function of the relative error in the frequency, the amplitude, and the period. And you get curves like this. And so if you want to get an infidelity of 10-3, so fidelity of 3 nines, you want to be here. For example, in this case, 2%, 3% for the frequency and the amplitude, and for the phase error, the order 1.8 degrees. Now, these are just for the accuracy, but you can do the same exercise for all sorts of errors, which includes both systematic errors like inaccuracies, so the deltas you can have, for example, due to limited resolution, but also due to random effects like noise. So frequency noise, amplitude noise, noise into time, that is jitter. And in this example I show you here, what we did, we basically assumed that all the budget of 10-3 infidelity is equally factored in all these noise sources. And that will mean that our, if you apply that pulse to an ideal qubit, you will get 99.9% fidelity. Now, of course, the point is that if you want to do a proper error budget, you want to allocate this error in a different ways on different error source, depending on how much this error source will cost you. For example, it's very easy to get very low noise, very low jitter in CMOS. It doesn't cost you much power, but the frequency or the amplitude noise costs you more. So you want to budget the noise in a way that you optimize your power consumption. And that's, the first step. Once you do that, then you can go to a proper architecture. In this case, basically, the basic architecture you want to build is an architecture in which you basically have a pulse in the digital domain, you convert to analog with a digital to analog converter, then you modulate with a microwave pulse so that you get your nice up-modulated pulse that you can send to a coaxial cable to the qubits to do the single qubit rotation. Now, if suppose a qubit 1 is tuned to frequency 1, you can tune any other qubits you have in your system to different frequencies so that you can sum up all your signals, all tuned to different frequency, and send to the same coaxial cable. So that with one driver, with one single coaxial cable, you can serve multiple qubits via frequency division multiple access, or FDMA. If you do that, you get into a number of extra challenges. Because first of all, if you have to serve multiple qubits, you need a wider bandwidth. That's one. Second, if you have a wider bandwidth, then you have to be careful that when you drive some qubits, for example, around here, you don't get spurious tone, which can do spurious rotation on other qubits, because they are all reactive to anything that happens on these bandwidths. And it's also true that if you try to generate, for example, a rectangular pulse simply on one qubit, that rectangular pulse could have a spectrum which could leak on the frequency of another qubit, generating again unwanted rotation. So one thing you want to do is, for example, pulse shaping. So if you would use a rectangular pulse, you get that the infidelity on a qubit, which is at a certain frequency space from your target qubit, you'll get that infidelity, of course, scales down as you move the qubits farther away, and this is on this scale as a function normalized to the Rabi frequency of the qubits. But in this example, to go to the 10⁻³ infidelity, you need to space them 30 times the Rabi frequency. A much better approach would be to use a much sharper frequency roll-off, for example, using a Gaussian envelope, which enables you to get within your maybe typical infidelity with only 4 times the Rabi frequency. And that enables you to pack more qubit channel in the same bandwidth. So you do that, but still you could have, due to the frequency shift, due to the energy at this part of the spectrum, you could get phase accumulation into idle qubits. So you have to compensate for that. Putting all those requirements together and assuming that you want to reach a 4/9 fidelity, just related to the error in the electronics, you come out with these requirements, which is a 1 GHz bandwidth that could be, in this range, if you want to target, depending on the spin qubit you want to target, a certain spurious-free dynamic range, so which tells how low the spurious needs to be, a certain signal-to-noise ratio, and more important, you should be able to have programmable pulse shape, duration, and phase correction. So all of this translates into an architecture in which you want basically to have a digital section and an analog section. In the digital section, you will have a number of numerically controlled oscillators which keep accumulating the phase and keep track of the phase of the qubits. Then once you select with the max the qubit you want to target, you generate a sine, you add the phase to the signal, you generate the sine and cosine signal. Eventually you do Z correction for correcting the phase on target qubits. You modulate with the amplitude, which is stored into a memory, and then you go to the analog domain when still in IQ fashion, you generate IQ channels, you up-modulate them, and you send to the qubits. And if you do all of that and implement that on CMOS, that's the system that you will have. You have a digital section in which you have all the instruction memory and the microcontroller to decide which instruction you need to send. You have the generation of the baseband signals in digital thanks to this numerical control oscillator. And then you have all the analog parts, which is in here is divided into the baseband and the RF parts. We did this in 22 nanometer FinFET technology from Intel. And the nice thing is that we proved that the chip is fully operational down to 3 Kelvin, so it can be placed close to the qubits. And in terms of power, we can spend, this is targeting 32 qubits, 32 qubit channels, with roughly a total of 10 milliwatt per qubit. So still far from the target we had in mind at the beginning. You know, this, remember, this 1 milliwatt per qubit, but we are getting into the ballpark there. In terms of flexibility, thanks to all this programmability, which is also cost you power, but you know, the advantage is that having all this digital interface and this programmability enables you to be able at an experiment time to really choose all the envelopes that you want. For example, here you see, and in the amplitude domain, a number of different waveforms you can generate, like cosine, raised cosine, rectangular, triangular, Gaussian, and the relative spectrum around 6 gigahertz in this example. The next step is to take, we know now that the system works, but can it really drive qubits? And in this experiment, we targeted 2 spin qubit system. You see it's shown in red and blue. And we first draw qubit Rabi oscillation into the red and blue qubits, and you were able to rotate the qubits in the block sphere. But what is interesting is to quantify if we really got the fidelity we wanted. And indeed, if we, this is the fidelity you would get using room temperature electronics. If you replace the cryogenic controller, you see that we are within the error margin at the same fidelity, which basically meaning that we are not limited by the Cryo-CMOS electronics, but by the qubits fidelity. And this is the case because we designed the electronics to be at the 4.9 levels. So that's how it should be. So this kind of doesn't tell us what is the fidelity that the electronics can support, but at least tell you that it's better than 99.7%. So this experiment was very successful. We were very happy that this worked. But one thing that we noticed doing this experiment is that if you take this die, we also put a couple of silicon diodes on the die to be able to monitor the on-chip temperature. And you see that as we increase the power consumption of our chip by, for example, increasing the activity by changing the clock of the digital, or doing more stuff in the chip, we could observe a different location of the die, an increase in temperature. And while the plate where the chip was connected, is still at maximum 5 Kelvin for almost 700 milliwatts power consumption, on chip you can get much higher temperature. So looking at this, we wanted to understand a little bit better what's going on. And we planned an experiment in which in a 40 nanometer test chip, we place a transistor shown here in the middle, where we can put quite some power. And then we use the gate of the transistor shown here as a thermistor, so as a resistive thermometer. So we can measure the current and the voltage and use it as a measure after calibration as a measure of temperature. And then we place sensing diodes across the device to understand what is the gradient of temperature around the device. So we wanted to measure what is typically called self-heating, how the device gets warmer. And in this plot, you see the self-heating measured at the gate of the device, which we assume be a proxy of the channel temperature of the device because it's only separated by a very thin oxide layer. And you see that these are the curves at all the way from 4 Kelvin up to 300 Kelvin in a color scale shown here. And you see that if we increase the power dissipating to a single transistor, you see we can easily get at 4 Kelvin almost 50 degrees of self-heating. So temperature is raising a lot. And as we will see, this can be because of a couple of problems. Because you think, the ambient temperature is 4 Kelvin, but your devices are not really at 4 Kelvin. They operate at much higher temperature, which has an impact on their performance. And also, if we look at the boundary, so this is the self-heating at a certain distance from the heating device. And you see that up to, in this zooming, up to even beyond 15 micron from the device, there is significant self-heating, at least of a few Kelvin. And that means that you have to be very careful because if you have one device in your circuit dissipate a lot of power, because it's maybe it has a lot of power to get low noise or to deliver some power to the qubits, all the surrounding can also get can also get hot, and that can be a problem because they can get out of the region of operation. This is happening also at room temperature, but can be more of a problem at cryogenic, because you get, at least relatively, you get going from 4 Kelvin to 40 Kelvin is relatively higher problem than going from 300 to 340, for example, for thermal noise. And we will see some effect of this in a moment. So this was a little bit an example of how you could generate how you can build electronics to drive the qubits. How can you exploit Cryo-CMOS to read out the qubits, for example, into doing RF readouts? Now, in this experiment, which was done in collaboration with Masoud Babai and the group of Lieven van der Sijpen. And by the way, also I forgot to mention, but I'll mention at the end. Also, the previous experiment was done in collaboration with these guys. So in this experiment, what we wanted to do was to probe a quantum processor made up of spin qubits by injecting tons of pulses into the quantum processor, and by measuring the transmission coefficient on this line, because the qubit couples to a certain line. By measuring what happens to the spectrum, you could measure if the qubit is in state 1 or state 0. And to do that, you need basically you need a low noise amplification, and then you need to down convert those pulses from around 6-7 gigahertz to basebands. And this was done in 40 nanometer. Notice that still, because the low noise, the performance of this circuit was not yet good enough, we also need a discrete Hempt LNA in front. And basically, what this circuit could do is indeed amplify signals both at room temperature in red and for Kelvin blue in a wide band from 6.5 to 8 gigahertz. And if you look at the noise performance measured as the noise figure, you see that, as you expect, the noise improves when you go from room temperature to 4 Kelvin. Now, you would expect, if it would be pure thermal noise, that this would decrease by the same ratio of the temperature. However, it's only 5x. And this, so it's not proportional to temperature. And this may hint on one side that you are limited by another source of noise, the shot noise, but maybe we are seeing here a sign of self-feeding. So the fact that although ambient temperature is 4K, the device temperature is much higher. So this could be a sign of that. So a little bit more modeling research is needed to really understand what's going on here, especially understanding better the noise of those devices. Now, having the system in place, what you want to do is, again, this was put in a dilution fridge, as shown here, and was used to measure quantum dots via this method. Now, without dealing a lot about the performance, what is interesting to notice is that the idea here is that since you are doing RF readouts, you could multiplex multiple channels. For example, if you use a readout bandwidth of 2 megahertz, you can put almost 400 qubit channel in this system, and then get a relatively low power budget per qubit, below 200 microwatts per qubit. So again, you are again in this ballpark of what you would need for the 1 milliwatt per qubit figure. Although, caveat here, you still have a discrete Hempt LNA, which is not included in this budget. After that, so you get your signal down converted to basebands, but you still want to go to your digital controller, and you need an analog to digital converter. Now there, what you want to do is basically take the full bandwidth of your signals, space and frequency, and try to down convert them. Now to do that, since you want to pack as many as qubits as you want to get a system which is very compact, you want to have a wide bandwidth. In this example, our requirements we put to ourselves was 1 gigasample per second, so we could have 500 megahertz bandwidth to down convert, which in this, using this assumption, we are able to fit 20 channels with 10 megahertz per channel and 10 megahertz channel spacing. And you need an effective number of bits between 6, 7, 8-ish. That's what you need. Now, how to reach that into an ADC? Well, the approach here, very briefly, was on one side, you wanted to get, as I said before, a power efficient system. And for this performance, the best performing ADC architecture is a SAR, a successive approximation architecture. So that's what we chose. Then we want to go for a relatively fast ADC, especially looking at the technology we want to use, which was 40 nanometer CMOS. So we used a couple of tricks to get as fast as we could. One is using loop unrolling, which is basically putting all the decision into different circuits in a row, and using 2 times interleaving. And then we had to take care that this circuit was operating properly down to 4 Kelvin. Now, the main thing that hit us in this circuit is the higher threshold voltage, which can limit the deadroom. And to deal with that, we adopted in the cap DAC at the input of the SAR, a specific switching scheme that enables all the comparator of the circuit to work at higher voltage range so that you have more space for the threshold. And also, as you may notice here, we use the high voltage 2.5 volt clocking because the switch here at the input use a thick oxide switch because we wanted to be very sure that the sampling could happen here. So that's why we used this trick here. And this chip was implemented in 40 nanometer. And it's interesting to look at the performance here, just to highlight some of the things that Cryo-CMOS can bring you or not. So in orange, you see the room temperature curves. In this chip, we can set the resolution from 6 to 7 to 8 bits. And depending on the setting, you can get higher signals to noise and distortion ratio as a function of the sampling speed of the ADC. And the blue is what happens when you bring it to 4 Kelvin. And what you clearly see is that you can extend the operation to higher sampling frequency. Basically, because I said before, going to cryo makes your circuit goes a little bit faster, not a hell of a lot faster, but here you get the same performance. Here you get around 800 megahertz. Here you get up to 1 gigasample per second, and you can get your almost 6 bits at 1 gigasample per second. Thanks to these techniques I showed you, we achieved relatively good specs in terms the efficiency of ADC is measured in energy per conversion step, which is a good number here. And more interesting for the application, you could see here that we try to replicate 20 channels in the bandwidth from 100 to 500 megahertz, and the ADC could convert them with enough SNR, resulting in less than 0.5 milliwatt per qubit. Okay, so now until now we have seen all systems that relied on RF signals going up and down those wires. So you have a microwave channel that is connected to microwave drive, which is connected to a coaxial cable going to qubits, and also a coaxial cable going up to this receiver. Also because these qubits are living at below 100 millikelvin, and the electronics was living at 4 Kelvin. So now let's look if we can get a little bit closer to the qubits. And we are exploring now how to do the gate biasing of a spin qubit processor. So for the gate biasing, you have your quantum dots here, and in a standard setup, you would connect each gate to a line that goes to a room temperature DAC. What we want to do now is to avoid all these interconnects, to simplify that, and basically bring all the electronics down to very close to the qubits, wherever the qubits are. Maybe you have a spin qubit operating at 20 millikelvin, maybe up to 1 Kelvin, but we want to bring them at the same temperature. And to do that, we use a multiplexer, which is basically used to sample the voltage generated by a DAC on a capacitor, so they can use a single DAC for all the gates. And basically, one thing we realized is that if the DAC just generates a ramp, including all the voltage you want to generate, the only thing you need to do is to sample each of these capacitors at the right time. So, for example, V2 you sample at time T2, and V1 at time T1. So with a single DAC, with a single slope, you can generate all the voltages required for all your quantum processor eventually. Also because these are DC signals, so you only have to counteract the leakage of your capacitors. You don't need to do it very fast. Typically, 1 Hertz rate for this is enough. And to do that, well, without going into much details, we used a switch capacitor integrator, so that generates a ramp, which is very always monotonic, which is good. So basically, you don't miss any codes. And then he has discrete step because it's switched cap, and that means it's easy to synchronize with the multiplexer. And then we use a couple of tricks to make sure that we have a wide output range. So we have a 3-volt output range in a process which maximally can handle 1.8 volts. And it's made reliable by using additional protecting device. Now, this DAC was able to, with only 157 megawatt power, was able to achieve 50-bit resolution on a 3-volt range with a nonlinearity below 2 millivolt, as shown here. And in terms of how much time does it take, so in the worst case, it will take 1 second to go from the low codes to the high codes. But you can also implement a nice trick where you can speed up the ramp. So you can do a fast ramp and then a slow ramp when you want to sample and go down to 20 millisecond latency. Them at least works. Now, what happens to a digital circuit when it works, but what happens to their performance when you push the temperature down? Typically, what you get is that going to low temperature, the circuit gets faster. But interestingly, if you plot the speed up, so how much faster you go than room temperature as a function of the technology nodes, the speed up goes less and less. And this is attributed to the fact that once you have older technology, you have more supply. So the fact mobility goes up, it makes you faster, which is good. But once you go to lower nodes, the supply is lower. And then you are dominated by the threshold voltage increase, which basically limits your performance. There are ways to get rid of that. But still, you don't get a big speed up. Now, so you get a little bit faster, but what about the power? Now, in a CMOS circuit, the power is basically depends on 3 different components. The dynamic power, the switching power, the short circuit power that is basically lost power, and the leakage power, so the power that leaks while you do nothing. These terms, when you go to cryo, is very little because the current goes so low for low VGS, you cannot even measure it, so it's typically negligible. The other 2 terms are limited by the frequency of operation, which is what you want to do, but are also limited by the supply. So one thing that we thought at a certain point is, okay, why don't we try to limit the supply, so to see how low you can go in power? And in this experiment, we try to design a digital libraries of cells optimized for Kelvin operation for using a number of tricks that could enable us to go to lower supply. And if you look to an example, this is 16 by 16-bit multipliers. And if you focus on the blue lines, you see that the cell we proposed could go at a lower voltage. So this is the frequency versus voltage at a lower voltage than the classical cells, but still you needed to operate at a much higher voltage than room temperature. And this mostly because the threshold was higher. So there was not, it was better than the classical at 4 Kelvin, but not better than 300 Kelvin. So we went also to try to build a full processor just to check how these things worked. So a RISC-V processor. And one thing we noticed is that indeed you can save power, but not by using lower supply. You save power. You see here, you're almost 2x saving power with respect to room temperature by the fact that since you go faster, you can reduce the supply and still be able to go fast. And the small reduction of supply enables you to save power. But still, we are not really getting to the improvement we really wanted using ultra low voltage supply. So that's still up to see how low can we go. Just an example of what we can use this digital supply for. Well, one possible application is to do a quantum error correction decoder in hardware. So it has been proven that if you have, your a surface code and you have the syndrome of your ancillas, you can feed them to a neural network, which will tell you, try to guess where the error happens. And well, in practice, it's much better to do it in this way, where you couple it to pure error decoder. But the final goal is really to build a neural network. And previous work tried to look at how to optimize this neural network in software. And what we did is, let's look what happens when you go to hardware. And for example, look at how the performance degrades for different surface codes when you change the number of bits in which you represent your weights, your memory inside the neural network. And using this technique, this is shown in a paper which recently was put on archive, we could show these trade-offs. These are trade-offs showing the pseudo threshold of the decoder for different surface code distances as a function of the cost, the hardware cost, which is the delay of the circuit, the area, and the power. And what you can see is that typically you can get this circuit to run very fast. That's a nice thing of neural network. In the 20 nanosecond level, you can run all of it. But you still may require a little bit of area and power. Without going into detail, we show that you can implement a number of decoders for a number of distances, even in FPGA, although it costs, may cost a little bit of power. But if you go on an ASIC, up to at least a distance of 5, you don't require a lot of area, and you can do with a reasonable power consumption. This is, an initial step toward the direction, but just to give an example of what you could do with digital. So just to come towards the conclusion, this is in a kind of an overview of all the different blocks that you will need to build if you want to make a scalable electrical interface, for example, for a spin-qubit quantum controller. Of course, different platforms, if you go to spin-qubit in diamonds, you need different things. But as an example, for spin-qubit in semiconductor, you will need, the microwave drive, the 2-qubit gates, the readout, but also a number of support electronics. So Ostrich was placed here. And one thing that sometimes people forget to mention is that still the qubits are often at much lower temperature, and there is quite a big gap in temperature between the electronics we are building and the qubits. And that, I think, is something that needs to be tackled in the coming future. For example, finding a better temperature on which to work. For example, 1 Kelvin. Okay, sorry for this. This went down. I don't know why. There are, in the group of Mennovel-Dors, in Australia, it was proven that qubit can work up to 1 Kelvin. So maybe going to an intermediate temperature would be better, but definitely the final goal would be to make a vision like this, where the qubits and the electronics can live and operate eventually on the same die, or at least in the same package. So to wrap up, so it's clear, I think, or at least I hope I convinced you that you need an electrical interface to make a quantum computer. And Cryo-CMOS is the technology that offers you very large scale of integration and cryogenic operation in an efficient ways. We demonstrated, us plus other groups in the world, several functionalities today using ad hoc design techniques often. Although basic design technique still work there. As an example of a complex SoC, I showed you Ostrich, where you have an algorithm fully driven by Cryo-CMOS without any deterioration qubit fidelity. And this is the typical design flow. So it's very important that you work very hard on the specification of the design. That's one of the most important parts here. Now, ongoing research to get a little bit of an idea where we are going is, on one side, we need to understand the model Cryo-CMOS device physics, at least some important aspects, for example, noise, self-fitting, optimize for power and area of those circuits. And eventually, at certain point, we'll need to optimize the full system, not getting the qubits as they are, but optimize qubit operation to make maybe the life of the electronic easier, or vice versa. And the current trend that I think we'll see more and more is how to get towards qubit electronics co-integration, which could be on the same chip, maybe on the same package. And this is relevant once you want to go to many qubits. But at the end of the day, I really believe that Cryo-CMOS will be an important enabler of large-scale quantum computers. And let not me forget to acknowledge all the people that contributed to this work. So this is most of the people in the group, and also thanks to Masoud Babai, Liven, Menno, and Giordano, and their teams for the collaboration that enabled a lot of this. Thanks a lot. And if there are any questions, happy to answer.
Thanks, Fabio, for this very inspiring talk. So indeed, we have quite some time for questions. If there are no questions, then I can kickstart. So you were mentioning this magic figure of 1 milliwatt per qubit when one has 1,000 qubits. But I guess at some point we will want not 1,000, but say 1 million. So what does this mean? We will have many blocks of 1,000, or there are some other way of accommodating?
Yeah, that's a very good question. I'm not sure I have a good answer to that, but I think there are two aspects to this problem. On one side, of course, you want to improve your power efficiency. But at a certain point, I think you will just hit, a bottom. There is a physical limit. For example, if you think in terms of low noise, there are some limits you cannot get better. But one thing we often forget is that you could expect that also the cooling power of the refrigerators could improve. For example, now, we are saying, okay, 1 watt at 4 Kelvin, just because the pulse tube in the dilution refrigerator we are using are those ones. You get, a few watts of cooling power. But eventually, if you imagine a system where, well, for example, like, if you look at diamond-based qubits, where you don't need to go maybe all the way down a lot below 1 Kelvin, maybe you can have a very different cooling solution. And next to that, as you said, there is quite some thought on using maybe multiple units. So if you have qubits that can operate still, as a full quantum computer, but being, spatially separated, that's a big advantage, because you could think of having multiple cold fingers, each cooling one section. So some sort of modular design that would help a lot, because at the end, we are really limited at the millikelvin level. But if you go to a few Kelvin, yeah, you can, well, I would not say easily, but you could get hundreds of kilowatts of cooling power. Yeah. So that's, I think, probably the way to go. So this, indeed, that's what I also believe. This 1 milliwatt per qubit is more like, nice number because it's round and nice, and for the short term is nice. But yeah, I don't think it's realistic to build a big computer with this number. Yeah.
Yeah, thanks a lot. More questions from the audience.
Hey there. Hey, thank you for your talk. I had a question about cryogenic electronics. Maybe I missed it. What are other applications except for quantum computing that might be interesting for these kind of?
Oh yeah, that's a very good one. So eventually there are some straightforward application. Could be some quantum sensors. For example, if you think to photon detectors. So a typical photon detector is SNSPDs. So this is based on superconducting nanowires. And eventually they have exactly the same problem. If you want to build an array, so you want to build an imager, right? Not like 10 pixel, but you want to build, n by n array. The limit is also the cabling. So you want to build the electronics down there. Other typical applications that are relevant could be, well, first of all the times you are in a cryogenic environment by itself. So space application is not so much, because although space is cold, typically on satellites or things like that, you get a lot of self-heating. So it's much warmer than 4 Kelvin typically. But there are, for example, in some system, you may use in some cryomechatronic system, you have superconducting coils that moves parts very fast, and you need a lot of current. And you want to collocate the electronics close by, because that's also an interesting thing. And one thing also people are looking a lot at is high performance computing, so supercomputers, but classical, but not based on quantum, but still maybe it could be even superconducting computers, or even CMOS cooled down. And for example, even for superconducting computers, one thing that people don't know how to do very well with this technology is memories. So it's very likely that this system will be hybrids, where you have a superconducting, maybe logic, maybe the RAM or the memory is CMOS. And then you need to make it also close. Maybe not at 4 Kelvin. Typically, this system works at 70 Kelvin or so. So these are just a couple of applications. But I should say that today, the big part of the research is really driven by quantum. This big, yeah.
Thanks. Clear.
A big push. Yeah. Thanks. Thanks for the question.
Hi, Fabio. Thanks for the talk. I have another question related to the last point, when you mentioned the integration between the quantum chip and the full processor. I mean, clearly we don't know yet if we're going to use which platform. Can be silicon germanium, can be silicon MOS, but maybe it's not likely that spin qubits are going to be defined in silicon MOS for the disorder. Do you see a possible? I mean, how do you see it possible to translate the technology that you are developing now in silicon MOS in another material, such as silicon or germanium electron gases, to make everything compatible, or is that to a higher request?
Yeah, that's a very good question. So I think, in general, the circuits we are building are, I mean, we are stuck to see, well, not we're stuck. We chose CMOS for the reason I said before, because this is the one that's where you get most development, because the semiconductor industry went for CMOS, then you have all this huge, improvement there, and then we rely on that. We're basically we just run with them in that sense. But if you think to it, once you take a transistor, a CMOS transistor on silicon, and you say, okay, you want to build on germanium, for example, or using a germanium quantum well, I don't think it will be worse. In fact, maybe it's even better. For example, like the thing you said, like the disorder, for example. So disorder is also a problem for classical electronics, flicker noise, aka charge noise, mismatch. These are all things that, comes from the interface. So it's not nice. So I think you could port to those. So I think that at the end, it's more than the device itself, especially if it's sort of a MOS kind of device. You don't have a big difference. So it's more the architecture you will learn. It's also true, I didn't talk about this now, but it could also be that you may need something a little bit fancier. Because, for example, for some blocks, we are seeing that some other devices like silicon germanium HBTs are, for example, very attractive for their performance. So, and other things I think is not only because, okay, I said, okay, we want to make on the same chip. Maybe on the same chip is a little bit too much. Maybe some needs to be on the same chip. So maybe some multiplexing is on the same chip, but then you need to go to sort of 3D integration for the full system. I mean, I think that's what we are doing also with classical system. Even classical microprocessors these days are 3D integrated. But yeah, that's a little bit, it's not a clear answer, but I think you could go there. I think you could go there.
Thanks.
Yeah.
So maybe it's not impossible, but it's just quite some work.
Yeah, the point is that you need to get very good transistor fabricated in those technologies. That's the first step. Once you get there, but well, definitely it could be a very nice experiment to try out how to, for example, implementing some simple multiplexer on those platforms. That could be very interesting. Yeah. But thanks for the question. Yeah.
Okay. Any other questions from the public? If not, then we are precisely on time. So then let's thank our speaker, Fabio, again.
Thanks a lot. Thanks, David. And thanks for the, attending, and thanks for the questions. Well, again, if you have, if this has triggered any questions, feel free, to reach me out by email or by person. I think it's nice to trigger some more discussion out of this. Thanks.